And so what I was talking about in the previous session, we started a problem from the topic of hypothesis testing, and we choose this testing of single proportion to be our case. And in that discussion, we found out the value of the standardized variable capital Z to be approximately equal to 5.36. And the formula that we actually used over there was given as x minus np by under square root over npq. Okay. Now, you see that if this were what I was telling in the previous session, that if this were just a problem of probability, then I could have stopped over there and I could have written that this is my answer. But this is just not the ordinary problem of probability. Okay, so the value that we have obtained is not our answer. We have to either reject, we are going to reject our null hypothesis, or we are going to accept our null hypothesis. Now, step one is done. Setting of null hypothesis is done. Setting of the parameters were done. Choosing of the appropriate tool was done. And by the way, that the one thing that I actually missed mentioning in the previous session is that the formula that I have used over here under this umbrella of testing of single proportion, such a formula in hypothesis testing is called, has a special name. It is called test statistic. You have to be very familiar about this particular notations and names in the hypothesis testing. So my test statistic used over here is of this form. The second important point is that how to draw we can call it as step number 3. Step number 3 is that once we get the value of the test statistic, once we get the value of test statistic, question is how to draw conclusion about the population. How to draw conclusion about the population. Okay. Now, here I am going to define some rules, and that I want to tell you about these rules. I want to tell that you are going to, if you want to do hypothesis testing, you have to keep these rules in your mind. Several steps are there. One after another, I'm going to discuss all the steps. In due time, I will, since you have seen that I'm not actually discussing the theory. I have started directly from the problem. And during the process, whatever is required, that I'm going to talk about. Okay. So right now, I'm going to talk about how to draw the conclusion. In this case, there are several different ways by which this can be done. Stepwise, algorithmic way, we actually do this. So one after another, I'm going to write these steps. The first step is this. The first step of drawing the conclusion is as follows. So I can write it as sub-step number 1. How to draw the conclusion. Sub-step number 1 says that once you calculate the value of Z, find mod Z. Calculate mod Z. Z is the normal variate. Remember. So I am actually trying to visualize the system from the perspective of this normal variate, standard normal variate. Now, when you are calculating capital Z, here in this particular case, Z has come out to be negative, positive. But it may so happen that in certain problems, the Z value becomes can become negative. So the Z value of your problem can either situate over here or can situate over there. But the conclusion part is saying that if you want to draw conclusion about the population, then you don't have to deal with both the parts of the normal curve. Try to find out the positive part only, and you can put out your conclusion on the basis of the analysis of the positive part only. Okay, so we are interested about the positive value of Z over here. So this is one of the rules I'm talking about. So first sub-step number 1 is mod Z equal to, you have to calculate mod Z. And as you can see that in our case, mod Z is nothing but equal to the value of Z itself, which is 5.36 itself. Substep number 2 is saying that once you calculate mod Z, check whether mod Z is greater than 3 or mod Z is less than or equal to 3. If mod Z is greater than 3, you are going to reject your null hypothesis always. Okay. And if mod Z is less than or equal to 3, then we have to decide about the acceptance of H0 on the basis of level of significance. This term, level of significance, is actually very important in the hypothesis testing. It plays a very significant role over here. I will explain level of significance in details in due time, but you have to know, you have to write somewhere this step that you have to decide that you cannot immediately, if mod Z is less than or equal to 3, you cannot decide immediately that what you are going to do about null hypothesis. You have to check it further. You have to check it further. Now, what does it actually mean? Diagrammatically, you can get a hint about this. For the time being, I'm saying that whenever I write mod Z is less than or equal to 3, technically it means that the Z value is lying between -3 and +3. So if you draw the normal curve, and if you consider the -3 value over there and +3 value over there, and if you find that it is falling inside this region, then you are not able to immediately put some kind of judgment over your acceptance of null hypothesis or not. You have to do something else. But if mod Z is greater than 3, that means either you are talking about this portion or you are talking about this portion. In hypothesis testing, these regions which I have marked red color and red colored and by green colored lines, these regions have some special names. The regions which I have marked by green colors, these are called acceptance region. And the region which I marked by red color are called rejection region or region of rejection. Similarly, this region of rejection is also sometimes called critical region. So when mod Z is greater than 3, that means your data is falling inside the domain of critical region, and therefore you are going to reject your null hypothesis straightforward. which is what in this particular case is happening. So you can see that for our case, your mod z is actually greater than 3. It's happening. It is happening that this data on the basis of which you are getting 3,240 throws out of 9,000 throw, that data is actually falling inside the critical region. And with respect to the substep 2, we are going to immediately declare that we reject the null hypothesis and we conclude that the given die is not unbiased. That is, P is not equal to 1/3. Actually, we are selecting H1 to be true. In this particular case, try to recall the problems that were given to you in the previous session. I do not have the question with me. Its question is not written on the board, but so far as I can remember, there were 2 parts of the problem. One part, in one part, we were asked whether we are going to reject or accept the null hypothesis, whether my dice is biased or unbiased one. We have actually answered that particular question. So this is my answer number 1. The question number 2 is that we were supposed to find the limits of between which the probability of 3 or 4 lies. That this question were asked in the second part. This question was asked in the second part. Okay, so we are going to answer to that particular problem. Now, since you didn't know about hypothesis testing, so probably we couldn't guess about you couldn't guess anything about question number 2, but question number 2 was actually a hint. The person who is well aware of hypothesis testing, after looking at the question, he will immediately understand that since the second part of the problem is asking me to find out the limits of the probability, limits between which the probability of 3 or 4 is lying, that means they are not sure about the population probability that they are assuming in the null hypothesis. But since you didn't have you didn't have this kind of experience, you couldn't guess it. That's why this question number 2 was valid, because in the part 1, the null hypothesis was going to be rejected. Now we know that capital P is the population proportion, and we are going to find out a limit within which this capital P will lie. Why? Because capital P has come out to be not equal to 1/3. The limits in which the population proportion capital P will lie will be given as P plus minus 3 under square root PQ by N. Another formula that I have used from estimation theory, and it is the topic which has been discussed, and you can check it in book in the chapter of interval estimation. This particular formula has been chosen from the chapter of interval estimation. This is the formula, and you have to recall, you have to memorize this particular formula. Now you see that when we are interested about this kind of limits, something like this, for this entity we are considering over here. Now this entity that we have considered over here, that is under square root capital P capital Q by small n. What is this? What is this entity? This entity is called the standard deviation of population proportion. In statistical hypothesis, it is sometimes also called, known as standard error of the parameter considered. So here the parameter is capital P. So this is the standard error of capital P. And in interval estimation, an estimation theory, this standard error of population proportion is given by the formula PQ by N. This is a formula that I'm actually using over here. Okay, so P will lie between. This means that we cannot guess the exact value of the population proportion in this case, but we can at least say that P will lie between these two numbers. This is the lower limit of population proportion. This is the upper limit of population proportion. And we're going to find these probabilities from our given values. But here comes the fact which I was discussing in the previous session. If I do not know about capital P, how can I calculate this probability? Because capital P is required, the value of capital P is required, the value of capital Q is required. So that's why I was saying that in one of my previous slides, that sample proportion, it has been correctly proved in estimation theory that sample proportion best estimates the population proportion. Okay, we do not know about capital P, but we know about the sample proportion. What is the sample proportion here? What is the sample proportion here? Out of 9,000 times, 3 or 4 is appearing 3 to 40 times. Sample proportion, if I denote sample proportion by small p, that is the formula, capital X by small n. And this sample proportion is actually estimating the population proportion. So we can say that estimated value of population proportion is the sample proportion. This notation is actually called estimated value of capital P. Okay, if capital P is like that, its counterpart capital Q cap, the estimated value of capital Q, will be given by 1 minus estimated value of capital P, which implies we can consider this to be Q minus 1 minus P. Okay, so accordingly, consequently, your formula this reduces to the following form. Since we do not know about this, we can rightly say that this implies capital P cap minus 3 estimated value of P multiplied by estimated value of Q divided by N. In this is the lower limit and this is the upper limit of the population proportion. And this in turn implies P minus 3 PQ by N less than or equal to capital P minus 3 PQ by N less than P plus, sorry, not minus this. Okay. Now you know capital P, you know small p, you can calculate this. Capital X is capital X by N is your small p, and which is 3240 by 9000. Okay. So what now you can do is that you can calculate this value, and consequently you can find the limit within which this population probability will lie for the unbiased type. So again, you try to find this out by yourself. You try to find this lower limit and try to find this upper limit and tell me what is coming over here. That will complete your calculation of the given problem. This part which I'm doing right now is not the hypothesis testing part. Hypothesis testing is done. We have rejected our dice. We have declared that the given die is not unbiased. It is a biased die. If it is a biased die, can we guess about the probability of getting 3 or 4? We cannot get a definite value for that, but at least we can find out a limit within which that will be lying. And that limit is what I'm calculating right now. So again, I am asking all of you to please calculate these values and tell me what you are getting. Yeah, someone is writing, Anjali Agarwal, she has got 0.345 as the lower limit and 0.375 as the upper limit. And that is your answer. That is your answer. Now, students, at this point, I want to ask you this question, that so far I am taking maximum amount of time to talk about a single problem, which I think will be helpful for you to understand the most of the things about hypothesis testing and its technicalities. Anjali, I'm asking, since Anjali has calculated this value, Anjali, you can write in the chat box. Have you understood the basic concept of what you are doing in this hypothesis testing? Or what so far what I have discussed, do you have any doubt in any part? Yeah, you have understood. So I am taking this reply of Anjali to be a general reply, and it is the overview, it is the viewpoint of the entire class. Okay, if anybody has any doubt in any particular phase, he can, or he or she can ask me. You can write in the chat box also. What I have not discussed in this particular problem is about what happens when mod z is less than or equal to 3. How can we further analyze the situation? That item has not been discussed yet. So I have not intentionally done so, because if I want to discuss theory, I can do it. I can discuss many theories, but let's wait for an appropriate problem. Once the problem comes in front of us, then with respect to the given problem, I'm going to discuss that. Let the situation come and then I'm going to discuss. So, okay, let's select another problem on hypothesis testing. And similarly, we shall approach over here. So example number 2, this time we are going to do it pretty quickly. Okay. So here is the problem for you. A random sample of 500 pineapples was taken from a large consignment and 65 were found to be bad, show that standard error of the proportion of bad ones in a sample of this size is 0.015, and deduce that the percentage of bad pineapples in the consignment almost certainly lies between 8.5 and 17.5. This problem you carefully observe. This is a part of the hypothesis testing problem. It is not a hypothesis testing problem. They are actually asking you to calculate some proportions about population proportions or sample proportions rather over here. So this problem is not a problem of hypothesis testing, because you are not going to test anything. Just they are actually checking whether you can identify this particular situation to be a situation of single proportion or not. Okay, so I am just writing what you can do with the given problem. I'm not going to do the problems in detail. 500 will be considered to be the sample size, so I'm writing here n. 65 were found to be bad, so this is my random variable, number of bad pineapples. This is capital X. You are going to calculate the standard error of proportion. Standard error of the proportion of what? Proportion of population proportion of bad ones, okay, in the sample. Now standard error, you know, the standard error of the proportion is actually given by the formula capital PQ by small n. And once, if capital P and capital Q are not known, it can be identified by PQ by n. This is the formula. So you can very well calculate this from here. Okay, you will get this as a result. This value will come out if you apply this formula, and small p is capital X by small n. And if it is so, you are going to calculate the limit, and here also you are going to apply this theorem which we applied in the previous case. So if you apply this, you are going to find this one lower limit to be 8.5 and upper limit to be 17.5. So in this particular problem, we are actually finding the technicalities of the calculations. It is not about hypothesis testing. So I'm not going to discuss this in details. You just take a screenshot of that quickly. I'm moving on to the next page. Let's try to find out from the exercise a problem of hypothesis testing. I have a problem sheet with me, which I actually created for one of my classes earlier. So I'm doing the exercise from that problem sheet. Probably you are thinking that from where I'm actually selecting the problem. From one of my earlier probability course, I actually selected a problem sheet. I'm going to share the problem sheet with you later on. Right now, I'm going to select this from here. Many problems are there in my problem sheet, and you will be able to practice a lot from here. First of all, let me make you familiar with this system. Otherwise, if you look at this large volume of problem which is there, then you may lose interest. In Jadavpur University, when we used to do our classes in Jadavpur University, the teacher used to release his problem sheet just after he introduces all the topics of the syllabus. And he used to talk like that, that he used to say that he didn't want us all, he didn't want all of us to I mean, shocked by the volume of the problem that are present in his problem sheet. So I'm just repeating his dialogue to you. That's it. Now, this is the problem you see. First of all, one thing that you, before you do any problem on hypothesis testing has very different types of domains. One of the domains that I started with today in today's class is the test of single proportion. You have only come to know about this particular test of single proportion. No other formula is known to you. So right now I have given a problem. So first of all, you have to check whether this particular problem is falling inside the domain of single proportion or not. Let us check it quickly. In a sample of 1,000 people in Maharashtra, 540 are rice eaters. So obviously this particular problem is talking about some sort of proportion. Immediately after that, and it is saying that the rest are wheat eaters. Okay. Immediately after saying that, it is asking a question whether we can consider this rice eating people and wheat eating people, they are equally popular. This rice and wheat are equally popular in the state. So that means they are actually talking about the population proportion of the rice eating people and population proportion of the wheat eating people. But they want to talk about whether these population proportions are similar or not. So therefore, this particular problem is obviously falling into the category of test of single proportion. It's not, there is no doubt about that, because you have only one sample. A sample is chosen, only one sample has been chosen. So obviously it is a test of single proportion. So first of all, as usual, we have to set up our null hypothesis. So we will write over here that let H0, rice and wheat are equally popular in the state of Maharashtra. That is, if capital P is the population proportion of rice eating people, you know, under the present circumstance, capital P, and since they are equally popular, so capital P can be considered to be equal to half. Okay. Similarly, H1 is rice and wheat are not popular, equally popular. And that implies capital P is not equal to half. And since this is your problem, this problem is falling into the category of test of single proportion. So under H0, you can choose your test statistic to be x minus n capital P by NPQ. This particular formula can be represented in another way. What you can do is that you can divide both the sides by both the numerator and denominator by small n, I'm going to show you another form of this particular, or you can directly substitute 1000 and capital P value over there, 540 over there. You can do it, or you can write it in this manner also. That is another form that you have to know about this particular problem. No, this small n that I'm writing over here, this small n will not be inside. The writing is wrong. It will not be inside the square root symbol. It will be outside the square root symbol. And you can write it as PQ by n root. Okay, so that is another form. Or you can write it as small p minus capital P by root over PQ by n. Either you can use this formula or another form of this. Both of them are same. You can substitute these values over there and quickly calculate. Substitute, all the values are given. So quickly calculate what is the value of Z. We do not have much time for today's class. Maybe I'll not be able to complete this particular problem in today's class, but at least let us try to find out up to this point, capital Z. In the next class, I'm going to continue from after that. Okay, so let us try to find out what is the value of capital Z over here. So I'm waiting for your reply. Time is running out. $2.5. Anjali, write up to 4 digit after decimal point. I always told you that you have to consider 4 digits after decimal point. It is a good practice. Is it 2.5 or are there any values after that? After 5, is there any other value? According to Anjali, it is approximately equal to 2. Okay, 2.5316. Okay, write it in this manner. Always, it is a good practice. 2.5316. Now you see, here you see, carefully observe that according to the steps that I discussed in the previous problem, substep number 1, I have to consider mod Z, which is definitely 2.5316 in this case. Substep number 2 reveals that now this mod Z is actually less than 3. We can't reject the null hypothesis immediately. We cannot reject the null hypothesis immediately. Let's stop over here. We are going to continue this particular problem with CSEB in the next week. Tomorrow I have a class with CSE section A, but this problem will not be discussed with them. I will discuss something else. Okay, something else related to hypothesis testing tomorrow. This will be continued with you in the next week, to be continued. Okay, so let's stop over here. Thank you for your participation. Okay, we shall meet once again in the next week in our scheduled hour. Thank you so much and good night.